Afternoon, everybody. Welcome to the fourth lecture on root locus. So, in earlier lectures, we have studied near about 5 rules to construct the root locus. The rule number 1 is that root locus is symmetrical about the real axis. The root locus starts from open loop poles with gain k is equal to 0, and root locus terminates either at open loop zeros with gain k is equal to infinity, or at infinity with gain k is equal to infinity. The root locus on the real axis that we can find via adding all the number of real poles and zeros to the right hand side of that point on the real axis. If that is even, if that is odd, then that root locus lies on the that part of the line segment lies on the root locus. Then the n minus m branches which are going to terminate at infinity, they will go along the direction of the asymptotes, whose angle of asymptotes is given by 2q plus 1 into 180 upon n minus m, where n is the number of open loop poles and m is the number of open loop zeros. The asymptote crosses the real axis at a point known as the centroid, which is given by minus sigma a. That can be calculated as sum of all the real parts of all open loop poles minus sum of all the real parts of open loop zeros divided by n minus n. This is what we have discussed in our earlier 3 lectures. Now today let us continue with the understanding of the construction of the rules. Now the rule number 6. Rule number 6 is about the breakaway point or break-in point. It is about breakaway point and break-in points. So it can be either a breakaway point or break-in points. So let's say this is one root locus branch. This is another root locus branch. They are approaching towards each other and they are meeting at one point. So as the k increases, the root locus branches move towards the right hand side. This branch move towards the left hand side. As the k increases, the k increases. Okay. And now they will meet at a point known as the breakaway point. This is the point which is known as the breakaway point. We can calculate this breakaway point also. Now this point occurs for a single value of k. There are multiple closed loop roots. Okay. So with that understanding, we can calculate the breakaway point or break-in point also. So after breakaway points, the root locus branches will move toward in the opposite directions. Now, so for that, we have a characteristic equation this. Now, this is a function of k. The characteristic equation is a function of k, because let's say g of s, h of s equals to, let's say, k into s plus 1 into, let's say, s plus 2, something like this. So, 1 plus g of s h of s is equal to 1 plus k upon s plus 1 into s plus 2. This implies that, and this is equal to 0, characteristic equation. So s plus 1 into s plus 2 plus k is equal to 0. So this is the characteristic equation, is a function of k. You can find like that, s square plus 3s plus s plus k is equal to 0. This is a function of the k. Now from the characteristic equation, I can find the breakaway point. How? So we know that the breakaway point is the point or a particular value of k for which there are multiple roots. As the two branches are approaching towards each other and they are meeting at one point, for that value of k there are multiple closed loop poles. So you can find, or and there are multiple closed loop poles, and moreover these poles, the direction of the root locus is changing after breakaway point, something like this. So the root locus branch is going this and this, they are approaching at this point, and then they are changing its slope, they are changing its directions. So I can find this point via taking the derivative of this, derivative of k with respect to s, and getting the maximum points or minimum points. So I will find k is equal to minus s square, then minus 3s minus s. This is equal to k. And now taking the derivative, that is dk by ds, and equating to 0 and solve this equation, we will get the breakaway point. So now dk by ds, so I can find minus 2s minus 3 is equal to 0. So minus 2s is equal to 3, and s is equal to minus 3 by 2 or minus 1.5. So s is equal to minus 1.5 in the s plane. This is the point, minus 1.5. This is the breakaway point. There can be multiple breakaway points also, or there can be many other solutions of this dk by ds equals to 0. You can discard some of the solutions which are not valid. How you can discard? You can look into the real axis. You have already calculated the portion or the line segment of the real axis which are the part of the root locus. So any solution which is not on the root locus, obviously that is not the breakaway point. So you can discard the breakaway points. There are some situations you may find where there can be a complex breakaway point also, but that you need to look carefully. So this is how you can find the breakaway point. So what is the procedure? Get the characteristic equation, put the characteristic equation in the form of k. So k is equal to something. Take the derivative dk by ds equal and put it equal to 0. Solve this equation and you will get the one of the breakaway points or multiple breakaway points. Discard the solutions which are not lying on the real axis. Means discard the real solutions which are not the part of the root locus. So this was about finding the breakaway point. Now let us see the sixth rule, which is about, or you can say seventh rule, which is about, actually it is about the seventh rule, that is angle of departure from complex open loop poles. This rule is 7a. This is 7a. There is another rule also, 7b, that we will discuss later on. So now this is about angle of departure from complex open loop poles. Now we know that the root locus starts from open loop poles. So this may be the S plane. There can be complex open loop poles also. There can be a real poles also. Now the root locus will start from this open loop pole. Now as far as the pole lies on the real axis, I don't have a problem because they will move either in this direction or in this directions. So their departing angle is completely known when the root locus, the pole, open loop pole is on the real axis. But I have a problem with these complex poles because the root locus may go in this direction, may go in this direction, may go in this direction, may go in this. There is 360-degree freedom for that root locus branch to move away from the open loop pole. So I don't know these directions. This direction is known as angle of departure. At what angle the root locus branch will depart from the complex pole? That is the rule. So to understand the angle of departure or to calculate the angle of departure for complex open loop poles, let us understand via one example. Once again, I want to make it clear that the angle of departure is for complex poles. It is not for the real poles, because for real poles the angle of departure is either 0 degree or 180 degree. Unless and until there are multiple poles, there are some situations. Now, so angle of departure, I am talking about 7th A rule, angle of departure is given by plus minus 2q plus 1 into 180 degree plus phi. Why it is plus minus? Because angle of departure is for complex poles. So there are two poles, they occur in complex conjugate pair. So one would be plus, another would be minus. So angle of departure is given by 2q plus 1 into 180 plus phi. And this phi, so everything is known, but phi is unknown. So what is phi? Phi is the net angle contribution to that open loop pole from open loop complex pole, I mean. Phi is the net angle contribution to that open loop complex pole from all other open loop poles and zeros. So angle of departure is given by plus minus 2q plus 1 into 180 plus phi. And phi you need to calculate. How you can calculate phi? Phi is the net angle contribution to that open loop complex pole from all other open loop poles and zeros. Let us understand this phi. Before that, let us understand what do you mean by angle contribution. So for example, so remember this line that phi is the net angle contribution to that open loop complex pole from all other open loop poles and zeros. Please remember this. So here that open loop pole, I mean for that open loop pole for which you are searching for the angle of departure, that is that number of pole. So that is one pole and other rest are other open loop poles and zeros. Now let us understand the angle contribution. So let's say this is my S plane and there is one pole here, there are two complex poles here, and let's say there is one zero here, there is one zero here. This is the situation. Now I want to find the angle of departure for these complex poles. If I can able to find the angle of departure for this complex pole, automatically the negative of that would be the angle of departure for this complex pole. So I don't need to calculate twice. If this is plus 70 degree angle of departure, this would be minus 70 degree angle of departure. Now let us understand the angle contributions. So this is that particular pole. Now I will draw a line with this. So this is the angle. Let's say this is phi 1. Then this is phi 2. Then this is phi 3. This is phi 4. So the angle contribution to this particular pole from this pole, this zero and this zero. So phi 1, phi 2, phi 3, phi 4. These are the individual angle contribution from all open loop pole and from all other open loop zeros to this particular pole. Now, how to calculate? Now, we know that the transfer function is about the zeros and poles. So, G of S, so G of S, H of S is given by open loop poles, zeros and open loop poles. So, angle of G of S, H of S is nothing but angle of open loop zeros minus angle of open loop poles. Now, you can see that angle contribution from zero is positive and angle contribution from poles is negative. Okay. This is a complex. So, if you want to find the angle contribution of G of S, H of S, then angle contribution of zeros minus angle contribution of poles. So, angle contribution from zeros is positive and angle contribution of poles is negative. So, now I have two zeros, phi 3 and phi 4. So, the angle contribution phi 3 and phi 4 would be positive and angle contribution from pole, that is phi 1 and phi 2, is negative. So, angle contribution or net angle contribution that is phi is given by net angle contribution from all poles and zeros. So, from poles, that is phi 1, phi 2, and that would be minus. So, minus phi 1 minus phi 2. This is the angle contribution from poles. Angle contribution from zeros, phi 3 and phi 4. So, plus phi 3 and plus phi 4. So, this is net phi. Now, you put this phi in this equation. That is 2q plus 1 into 180 plus phi. Phi is the net angle contribution. You have calculated net angle contribution like this. And you will get the angle of departure. Once you get the angle of departure for this pole, automatically the negative of that is the angle contribution, is the angle of departure for this pole. So, you don't need to calculate twice. So, this is how we can calculate the angle of departure for complex poles. Now, I am talking about rule number 7b. That is angle of arrival to complex open loop zeros. So, we know that the root locus is departed from complex poles. So, that's why I need an angle of departure. An angle of departure is always for poles because from where the open loop branch is departed. Now, some of the branches, the n number of branches are actually, they have started moving inside the S plane. Out of that n number of branch, the m number of branches means number of zeros. These many branches, m number of branches, they are going to terminate at open loop zeros. So, a branch starts from pole and terminates at open loop zeros. Okay, or else it can terminate to infinity. If there are n number of poles and there are m number of zeros, then out of those n number of branches, m number of branches will go to the zeros. But rest n minus m branches will terminate at infinity. These infinity branches, they will go along the direction of asymptotes. So, if the number of poles and number of zeros are equal, then there is no asymptote. And you don't need to calculate angle of asymptotes or neither centroid you need to calculate. So, I am talking about these m branches which are going to terminate at zeros. For these, the angle of arrival is required, because from which direction the root locus will arrive to the open loop zeros. That is required. So let's say a branch is coming from any open loop pole, I don't know, and it is terminating at this 0. So for real zeros, you don't have to worry, because they will come either from negative, they will come from 180 degree or from the 0 degree. So if the 0 is lying on the real axis, it will come from this way or it will come from this way. I don't need to worry about the angle of arrival for real zeros. But I am talking about complex zero. So this is a complex zero, and any root locus, any branch which is it is coming to this 0, at what angle it will arrive to the complex 0? That is known as angle of the arrival. So I need to calculate the angle of arrival also. So for that, the formula is angle of arrival is given by plus minus 2 cube plus 1 into 180. See, there is no, if you put q is equal to 0, if you put q is equal to 1, then it will move a 360 again. You will get the same answer. Okay. So if you put q is equal to 0, answer would be same. 1 also answer would be same. 2 also answer would be same, because it will take one round of 360 degree. So don't worry about q. So angle of arrival is equal to plus minus 2q plus 1 into 180 degree minus phi. Note that earlier it was plus phi. Now for angle of departure it was plus phi. Angle of arrival it is minus phi. And phi is net angle contribution to that particular 0 See, earlier it was pole, now it is that particular 0 from rest all open loop poles and zeros. So now I need to concentrate on 0. So let us take an example to calculate the phi. So let's say open loop poles are, let's say here, let's say there is one 0 here, there is one 0 here, and there is a pole here and here. Now I need to calculate angle of arrival. Angle of arrival is for complex zeros. So here. So if you can calculate the angle of arrival for this 0, automatically the negative of that would be the angle of arrival for this 0. So I need to calculate this. So I need to take the angle contribution. So let's say this is phi 1, phi 2, phi 3, phi 4. Okay, yeah. So phi 1, I forget this. Let's say this is phi 5. So we know that phi 1, phi 3, phi 2, phi 3, phi 1, phi 2, phi 3, phi 4, they are due to poles, and phi 5 is due to 0. So angle contribution from 0 is positive, angle contribution from pole is negative. So phi is given by phi 5 minus phi 1 minus phi 2 minus phi 3 minus phi 4. This is the net angle contribution. So angle of arrival can be calculated via plus minus 2q plus 1 into 180 minus phi. So phi is this. This is how you can calculate the angle of departure, arrival for complex zeros. Now, the next rule is the 8th rule. it is that the root locus crossing imaginary axis. So far we know what is the starting of the root locus, from where it will start, from where it will end, and where it will break also, what are the angle of departure also, where the root locus on the real axis. Now, let's say this is the root locus. Let's say this is the root locus. Now it crosses the j omega axis. So where it can cross the j omega axis? So I need to find this point or this point. This is known as root locus crossing the imaginary axis. So this is the point where, so there would be a particular value of k for which the root locus crosses the imaginary axis. So this is very important as far as the stability is concerned, because for this value of k the root locus will stable, and for this value of k the root locus is unstable. As soon as root locus crossing the imaginary axis and it goes from left hand side of S plane to right hand side of S plane, the system becomes unstable. So this is the margin of stability that we are getting as far as the gain k is concerned. So for this value of k, I can say that I need to increase that value of k. Beyond that, the system becomes unstable. So I need to find this point, that is the root locus on the imaginary axis, or root locus crossing the imaginary axis. I think to calculate this, that we have already studied actually this. We have studied the Raoult-Harvey's criteria for checking the stability of the system. So what we were doing in Raoult-Harvey's criteria, we start with the characteristic equation. So 1 plus g of s h of s equals to 0, and this is the function of k, and we prepare the Raoult table. Now we prepare the Raoult table and we ensure that the first column of the Raoult table is, the elements of the first column of the Raoult table are positive. This means the system is stable. Now as soon as the root locus crosses the imaginary axis, it means that there are multiple poles on the imaginary axis. So we have discussed the case number 3 in the Raoult table, that when the entire row of the particular Raoult table is 0. So when the entire row of the Raoult table is 0, it means that there are multiple roots on the imaginary axis, or there can be a pair of the roots on the imaginary axis. So we use the case number 3 of the Raoult table, that is entire row is 0. To find these points, because these are the multiple poles. Alright, let us understand via example. So let's say there is an open loop transfer function k into s plus 3. This is g of s, h of s equals to s into s plus 1 into s plus 2, and let's say I take another pole, that is s plus 4. This is the open loop transfer function. And for this, you can calculate the angle of the asymptotes. Angle of asymptotes 2k plus 1 into 180 upon n minus m. This you will get angle of asymptotes. You will get 60 degree, 180 degree, 300 degree. And let us calculate the centroid, which is given by minus 1, minus 2, minus 4. Okay. And minus sum of the real parts of poles minus sum of the real parts of zeros upon 1, 2, 3, 4, 4 number of poles and 1 number of zeros. So this actually you will get minus 4 by 3. Okay. So this is the angle of arrival. The angle of asymptotes and the centroid. Now you can find the breakaway points also. Breakaway points. So 1 plus g of s, h of s equals to 0. So you will get the characteristic equation the characteristic equation is something like this. That is 1 plus s raised to 4 plus 7s cube plus 14s square plus 8 plus k into s plus 3k. And now you find the value of k something and then put dk by ds equals to 0 and find the roots. The roots are actually, you will get the roots as s is equal to minus 1.45 and you will find s is equal to 3.82. So these are the solutions of this, and now you need to identify which out of these roots, which are the breakaway points, those which are lying on the real axis, and moreover they lie on the line segment of the root locus. You need to identify that. From this you can find the angle the breakaway points. Now let us calculate that when the root locus crosses the imaginary axis. So for that you need to calculate the characteristic equation, that is 1 plus g of s h of s 0 from this. So I am writing the characteristic equation, that is s raised to 4 plus 7s cube plus 14s square plus 8 plus ks plus 3k. This which is equal to 0. Now you prepare the route table. So preparing the route table starts from s raised to 4. You take alternate coefficients. So 1, 14, then 3k, then s raised to cube. You put this, that is 7, 8 plus k, and if there is no coefficient you put 0. Then comes s raised to 2. So this into this minus this into this divided by this. So this is 90 minus k, this is 21k, then s raised to 1. So this into this minus this into this divided by 90 minus k. So this comes to minus k square minus 65k plus 720 divided by 90 minus k, and this goes to 0. Then s raised to 0. So this into this, sorry, here there is 21k, here there is 21k, okay, 90k, 21k. So this into this minus this, so you will get 21k. So this is the first column of the route table. Now you want that entire row to be 0. So this cannot be 0, this row cannot be 0, this row also cannot be 0, but you can say that this row can be 0 if this is equal to 0. If this term equals to 0, then the entire row is 0. It means that there are multiple roots on the imaginary axis, and that is what we are intent to do that. So if this is equal to 0, then this means minus k square minus 65k minus k square minus 65k plus 720 is equal to 0. So you can solve this to get the value of k, and here the k is 9.65. If this is the k 9.65, the row which is the entire row is 0, the above row is known as the, you can find the auxiliary polynomial from the above row, that is from s raised to 2 row. So I will find the auxiliary polynomial, that is auxiliary polynomial is 90 minus k into s square plus 21k is equal to 0. You get the value of k, replace this. So auxiliary polynomial becomes 80.35 s square plus 202.7 is equal to 0. If the auxiliary polynomial equals to 0, you solve for auxiliary polynomial, you will get the roots. So if you solve this, you will get s1, s2 as plus minus 1.59j. So now this was the root locus, for example, and this is plus 1.59j and this is minus 1.59j. The solution of the auxiliary polynomial, that is two roots 1.5 plus minus 1.59, are the roots or are the closed loop poles which are on the imaginary axis. So this is how you can find that when the root locus will cross the imaginary axis, at what point. You can find the value of k also from that. So today let us summarize this lecture. Today we have discussed the breakaway point, that is dk by ds equals to 0. So from you get the characteristic equation, arrange the characteristic equation in the form of k, take the derivative with respect to s, that is dk by ds, equate to 0. In solve that, you solve for the dk by ds equals to 0, you will get the breakaway points. Identify the correct breakaway points. Then angle of departure from complex poles and angle of arrival from complex two complex zeros. And then we have discussed the important rule, which is the angle, the root locus crossing the imaginary axis, that can be done via Raoult-Hurwitz. So you prepare the characteristic equation, prepare the Raoult table, make one row 0, which is possible. Here it is s raised to 1. So identify the row which is equal, where all the entire elements are, the complete row becomes 0, and get the value of k. Replace the value of k in the auxiliary polynomial, which is the above, can be constructed from the coefficient of the above row, and solve the auxiliary polynomial. You will get the closed loop poles which are on the imaginary axis. Thank you, and I have uploaded some of the material on the LMS also regarding the root locus. Thank you.